On this tranquil evening, let us embark together on a tender cosmic odyssey. Close your eyes and envision yourself drifting through the boundless depths of space, enveloped by twinkling starlight, each celestial beacon softly narrating the ancient tales of our universe. In the remote depths of space, a special golden eye quietly observes the cosmos's deepest secrets. This is the James Webb Space Telescope, a celestial observer born from decades of human dedication and $10 billion in investment. Like a patient cosmic sentinel, it methodically gathers every precious photon from distant galaxies. The telescope's genesis reads like a tender miracle. Initially conceived in the 1990s with a modest $1 billion budget and a planned 2007 launch, this project, much like nurturing a rare flower, weathered countless setbacks and postponements until finally taking flight in December 2021. Picture this 6,500-kilogram cosmic behemoth with its sun shield spanning 14 by 21 meters, nearly matching a standard tennis court's dimensions. This sun shield resembles a celestial bloom composed of 5 gossamer layers, each as delicate as butterfly wings yet remarkably resilient. When it gracefully unfolds in the vacuum of space, we witness a massive cosmic butterfly gradually spreading its wings with breathtaking elegance and precision. Webb's primary mirror comprises 18 hexagonal segments with a combined area 6 times larger than Hubble's. Each segment bears a whisper-thin gold coating, not merely for beauty, but because gold provides perfect infrared reflection. Bathed in sunlight, these segments form 18 golden petals, creating a luminous flower blooming in the cosmic garden. Webb's extraordinary capability lies in detecting infrared radiation, those tender wavelengths invisible to human perception. Due to cosmic expansion, light from the most distant galaxies stretches into infrared during its epic journey. It's as if the universe whispers ancient secrets that only the most sensitive instruments can detect. To clearly capture these cosmic murmurs, Webb must maintain extraordinarily low temperatures, approximately -223 degrees Celsius, a mere 50 degrees above absolute zero. Imagine a virtuoso musician listening for the faintest melodies in perfect silence. Any thermal emission from the telescope itself would contaminate these delicate observations, much as noise would mask a beautiful symphony. To achieve such frigid conditions, Webb orbits at Lagrange point L2, 1.5 million kilometers from Earth. At this gravitational equilibrium, Earth and Sun's forces balance perfectly, allowing the telescope to maintain synchronous orbit while perpetually facing away from our star, working serenely in the universe's shadow. Deep in space, 7,600 light-years distant, lies an enchanting region known as the Cosmic Cliffs. NGC 3324, nestled within the Carina Nebula, reveals unprecedented splendor through Webb's infrared vision. These so-called cliffs are actually towering walls of gas and dust, soaring 7 light-years high. Traveling at light speed, crossing from base to summit would require 7 full years. Envision heights equivalent to twice the distance separating our solar system from Proxima Centauri. Through Webb's gaze, these cliffs display dreamlike amber and crimson hues, reminiscent of the Grand Canyon at sunset, yet on scales beyond human comprehension. Along this cosmic canvas's edge, an invisible battle rages. Fierce stellar winds from newborn stars act like celestial hurricanes, relentlessly sculpting nearby gas and dust into these spectacular cliff formations. This cosmic artistry has continued for millions of years, nature's sculptor patiently crafting a masterpiece of unimaginable scale. Webb's remarkable sensitivity allows us to peer through these dusty veils and glimpse hidden secrets within. In these seemingly barren regions, the universe's most magical process unfolds: stellar genesis. Much like seeds silently sprouting in fertile soil, cosmic dust and gas gradually coalesce under gravity's tender embrace, eventually igniting nuclear fusion and becoming luminous beacons in the darkness. Webb's mid-infrared instrument functions like a cosmic obstetrician, seeing through dense dust clouds to witness these stellar births. Each nascent star remains cocooned in its dusty chrysalis, awaiting the moment to emerge as a brilliant celestial butterfly. Compared to Hubble's observations, Webb unveils extraordinary detail. Where Hubble perceives dust-obscured silhouettes, Webb reveals crisp star-forming regions, each bright point potentially harboring a developing solar system. These discoveries provide astronomers with invaluable data for studying stellar formation, helping us understand how stars like our Sun are born. At the relatively nearby distance of 2,000 light-years, a magnificent celestial object called the Southern Ring Nebula awaits our exploration. NGC 3132 resembles a colossal cosmic eye, serenely gazing into space's depths while narrating the poignant story of stellar twilight. Once, a star dwelt here, warm and radiant like our Sun, burning steadily for billions of years. Yet just as humans age, stars follow their own life cycles. As this stellar giant slowly aged, its nuclear fuel dwindled, causing outer layers to expand and contract erratically, like an elderly person's labored breathing. In life's final act, this star began shedding its outer layers, resembling autumn leaves gracefully cascading earthward. Rather than death, this represents beautiful rebirth. These expelled materials, rich in heavy elements, carbon, nitrogen, oxygen, serve as life's fundamental building blocks. Under starlight's illumination, they emit a soft blue-green radiance, forming an exquisite halo spanning half a light-year. Webb's dual instruments, the near-infrared camera and mid-infrared instrument, reveal two distinct aspects of this celestial marvel. The near-infrared camera maps hot gas distribution, exposing intricate structures and details like an X-ray revealing skeletal architecture. Meanwhile, the mid-infrared instrument unveils dust and molecular information, akin to observing cellular internal structure. Combining these observational perspectives, scientists uncovered a startling revelation. This planetary nebula emerges from a binary star system. Beyond the visible dying white dwarf, a companion star continues burning normally. This companion's gravitational influence shapes gas flow, creating elaborate spiral patterns like two dancers locked in an eternal cosmic waltz. Even more intriguingly, this second star hasn't reached life's end, and its own planetary nebula may eventually form. When that moment arrives, we might witness a double cosmic wreath, with two stellar legacies intertwining to create even more complex and breathtaking structures. In the Large Magellanic Cloud, 161,000 light-years distant, a colossal star factory known as the Tarantula Nebula operates at full capacity. NGC 2070 resembles a gigantic celestial arachnid, weaving stellar webs across space, each strand composed of incandescent gas and newborn stars. This nebula earned its tarantula designation from gas filaments radiating outward, mimicking spider web fibers. Unlike terrestrial spider webs, these strands span dozens of light-years, far exceeding our solar system's diameter. The Tarantula Nebula ranks among the most vigorous star-forming regions known to astronomy. Here, stellar birth occurs at breathtaking pace, like a spring garden suddenly erupting with countless blossoms. Within mere millions of years, an instant by cosmic standards, tens of thousands of new stars emerge. This region evokes memories of a special cosmic epoch, cosmic noon. During this period, roughly 1 to 3 billion years post-Big Bang, star formation reached unprecedented peaks. The entire universe resembled a vast stellar foundry, producing luminous sources at astounding rates. The Tarantula Nebula serves as a contemporary window into that primordial era, allowing direct observation of the universe's adolescent phase. Through Webb's infrared perception, we observe infant stars that have just ignited nuclear fusion. Many remain shrouded in dense dust clouds, like newborns wrapped in cosmic swaddling. Intense radiation from these stellar infants gradually disperses surrounding dust, reminiscent of morning sun burning away fog. The Tarantula Nebula also harbors true stellar titans, stars potentially tens or hundreds of times more massive than our Sun. These giants burn like cosmic fireworks, radiating intensely but living briefly. They'll exhaust their fuel within millions of years, eventually culminating in spectacular supernova explosions that scatter heavy elements throughout space. Webb's observations reveal intricate details of stellar formation processes. We observe accretion disks surrounding protostars, material streams being drawn inward, alongside gas jets expelled by powerful stellar winds. Each detail serves as a clue, helping scientists assemble the complete puzzle of stellar birth. At 290 million light-years distance, 5 galaxies perform an elegant cosmic ballet, the renowned Stephan's Quintet. Though one galaxy proves merely a visual illusion, positioned much closer but appearing aligned by perspective, the remaining 4 dance together in gravitational embrace. This galactic ensemble gained fame through the classic film It's a Wonderful Life, yet its true magnificence lies in showcasing one of the universe's most spectacular phenomena, galactic collisions. Envision 2 enormous galactic metropolises, each containing hundreds of billions of stellar citizens, slowly converging as their skyscrapers, star systems, become caught in this cosmic merger. Webb's observations clearly reveal 2 galaxies already locked in gravitational interaction. Superheated gas and dust stream into space, forming elegant arcs and elongated tidal tails like celestial fireworks frozen in time. Though this moment spans tens of millions of years, the gravitational choreography surrounding these interacting galaxies creates unprecedented complexity. We witness gas streams writhing through space, forming spiral arms and graceful arcs. In certain regions, gas compression reaches such intensity that it triggers fresh waves of star formation. Cosmic pyrotechnics on a galactic scale. Webb's image represents a technical tour de force. This cosmic puzzle emerges from nearly 1,000 individual exposures, each composed of photons patiently harvested by Webb. Like a meticulous artist creating a masterpiece stroke by stroke, this mosaic technique reveals unprecedented detail across every scale, from individual stars to massive gas clouds. Such galactic encounters occur regularly throughout cosmic history. Indeed, our Milky Way will merge with Andromeda Galaxy in approximately 4.5 billion years. When that epoch arrives, our night sky will transform completely, though this process unfolds so gradually that Earth's inhabitants would scarcely notice the change. Now, let us direct our attention toward even more distant realms, where the universe's most ancient secrets lie hidden. In a minute patch of sky designated Webb's first deep field, the telescope has opened a window into the cosmos's infancy. This observational area appears incredibly tiny. Extending your arm and using a sand grain as a mask would completely obscure this celestial region. This roughly equals the angular size of a small lunar crater viewed from Earth. Yet within this minuscule window, Webb discovered thousands of distant galaxies, each representing a complete cosmic island harboring billions to trillions of stars. This deep field image showcases gravitational lensing in spectacular fashion. The foreground galaxy clusters immense mass warps light from more distant galaxies, functioning like a natural cosmic magnifying glass. This phenomenon creates stunning arcs and rings, transforming distant galaxies into wonderfully distorted shapes. Among these twisted light rays lurks a particularly ancient crimson speck. This diminutive galaxy's light has traversed the universe for 13.1 billion years. When this photonic journey commenced, the cosmos remained in its youth, less than 1/10 its current age. The first stellar generation had barely begun illuminating the universe. Heavy elements remained scarce, and the entire cosmos bore little resemblance to today's majesty. It's like receiving correspondence from antiquity. The parchment yellowed, the script faded, yet still conveying precious tales of the universe's childhood. By analyzing these ancient light spectra, scientists can decipher the early universe's chemical composition, temperature, and stellar formation rates. Webb's efficiency proves even more remarkable. Hubble required 10 full days of exposure, slowly accumulating photons from this region to create its deep field image. Webb captured this photograph in merely 12 hours while revealing richer detail and discovering more galaxies. Like a virtuoso photographer capturing in moments what others require hours to record. What does this efficiency breakthrough signify? If Webb conducted a 10-day exposure, how deeply could it penetrate the cosmos? How many more ancient galaxies might it discover? Future observations will gradually answer these questions, but we stand confidently at the threshold of a new astronomical era. This deep field image also reveals cosmic evolution's timeline. Nearby galaxies appear large and mature, displaying complex structures and relatively blue hues, evidence of ongoing star formation. More distant galaxies seem smaller, redder, and more irregular hallmarks of the young universe. By observing galaxies at various distances, we're essentially viewing cosmic snapshots across different ages, like browsing through the universe's photo album. Within our Milky Way's tender embrace, 3,800 light-years from Earth, a magnificent cosmic butterfly slowly unfurls its wings. NGC 6302, lovingly dubbed the Butterfly Nebula by astronomers, resembles the most exquisite embroidery adorning the universe's dark velvet tapestry. This celestial butterfly's wingspan exceeds 3 light-years, surpassing 3/4 of the distance from our Sun to Proxima Centauri. Traveling at light speed, journeying from wingtip to wingtip would consume 3 full years. These wings consist of superheated gas expelled by a dying star, expanding through space at hundreds of kilometers per second, creating this spectacular bilateral structure. The Butterfly Nebula's chromatic palette provides its most enchanting feature. Azure and turquoise luminescence emanates from ionized oxygen atoms, like enchanted dust scattered by celestial fairies. Purple regions result from glowing hydrogen, while crimson areas showcase nitrogen's contribution. Each hue represents distinct temperatures and chemical compositions, combining like a cosmic stained glass cathedral window. For 2,200 years, these gaseous wings have expanded through space, continuously sculpting new magnificent forms. This process continues presently, meaning the Butterfly Nebula transforms before our very eyes. It resembles watching a flower bloom in time-lapse photography, except this time-lapse spans millennia. Hubble Space Telescope's recent observations unveil unprecedented intricate details within the Butterfly Nebula. At the wing's center, we discern complex knotted structures and jets, all evidence of the central star's vigorous activity. This star, concealed within dense dust clouds, remains highly active, its intense stellar winds sculpting surrounding material into these delicate structures. 8,000 light-years away in deep space lies a stellar nursery called Pismis 24. This cosmic cradle teems with newly born young stars whose radiance illuminates the surrounding vast gaseous ocean. Though Pismis 24's name may sound unfamiliar, it enjoys considerable fame within astronomical circles. Pismis 24 resides within the larger emission nebula NGC 6357, bearing the more poetic moniker Lobster Nebula due to its crustacean-like silhouette. The entire region brims with nascent stars and intricate gaseous architecture. These azure stellar infants burn far hotter and more massively than our Sun. Their masses exceed solar mass by at least threefold, with some reaching several dozen solar masses. These giants' surface temperatures soar to 30,000 to 50,000 Kelvin, dwarfing our Sun's modest 5,800 Kelvin. Such extreme temperatures generate their characteristic intense blue-white luminescence. Fierce ultraviolet radiation from these young stars acts like miniature cosmic suns, illuminating surrounding hydrogen clouds. When ultraviolet photons strike hydrogen atoms, they strip electrons from nuclei, a process termed ionization. As these ionized hydrogen atoms recapture electrons, they emit characteristic red light, creating the beautiful crimson regions adorning the nebula. Within Pismis 24 dwells a star once considered the most massive ever discovered, Pismis 24-1. Initially, astronomers estimated its mass approaching 300 solar masses, potentially shattering all stellar mass records. However, subsequent high-resolution observations revealed this as actually a multiple star system comprising at least 3 stars, each weighing approximately 100 solar masses. Though not achieving the initially estimated staggering mass, they remain among the universe's heaviest stars. These stellar nurseries nestle within warm gaseous clouds, like soft cradles prepared for newborn stellar infants. These clouds, termed HII regions, serve as active stellar birthplaces. Here, dense molecular clouds begin collapsing under their own gravity, with rising temperature and pressure eventually triggering nuclear fusion. Thus, a new star is born. Yet these giants face brief but brilliant destinies. Due to their prodigious fuel consumption, they sustain life for mere millions of years, contrasting sharply with stars like our Sun, which burn steadily for 10 billion years. When these titans exhaust their fuel, they'll perish in magnificent supernova explosions, seeding surrounding space with heavy elements that become raw materials for future stellar and planetary generations. At the Milky Way's halo edge, a wandering globular cluster drifts in cosmic solitude. Palomar 12 resembles a lost child originally belonging to the Sagittarius dwarf elliptical galaxy family, yet adopted by our Milky Way through a cosmic kidnapping event approximately 1.7 billion years ago. This cluster's discovery story brims with drama. In 1955, astronomer George Abel identified this fuzzy object on photographic plates at Palomar Observatory. Initially presumed to be a Milky Way native, advancing observational technology revealed unusual characteristics. This cluster stars appeared roughly 30% younger than other Milky Way globular cluster inhabitants, with distinctly different chemical signatures. Like suddenly discovering vibrant youth in an ancient community, their behavior revealing foreign cultural backgrounds. Further investigation confirmed suspicions. Palomar 12 was indeed an outsider, its true homeland being the Sagittarius dwarf elliptical galaxy. The Sagittarius dwarf elliptical galaxy orbits our Milky Way much as the Moon circles Earth. However, this orbit remains dynamic. Gravitational interactions gradually modify trajectories. Over eons, the Sagittarius dwarf repeatedly approaches the Milky Way, each encounter subjecting it to powerful tidal forces. Imagine oceanic tides influenced by lunar gravity, but on galactic scales. When the Sagittarius dwarf traverses the Milky Way's core region, our galaxy's enormous gravity stretches and deforms it like manipulating cosmic putty. During this process, clusters and stars become stripped from their parent galaxy, joining the Milky Way as new citizens. Palomar 12 experienced such cosmic kidnapping. Now it orbits peacefully within the Milky Way's halo, approximately 130,000 light-years from our galactic center, fully adapted to its new cosmic home. It contains tens of thousands of stars, all now Milky Way citizens despite bearing their distant homeland's chemical fingerprints. Such intergalactic adoption events occur regularly throughout the universe. Many Milky Way globular clusters likely share similar origins. By studying these immigrant clusters, astronomers trace the Milky Way's growth history and understand how larger galaxies absorb smaller ones. These investigations reveal a fundamental cosmic truth. Under gravity's influence, cosmic structures constantly evolve, small absorbed by large, weak assimilated by strong, representing universal evolution's basic principles. 30 million light-years away, an elegant galaxy displays its magnificent profile. M104, affectionately known as the Sombrero Galaxy, resembles a distinguished lady wearing a broad-brimmed hat, gracefully dancing at a cosmic soiree. The Sombrero Galaxy earns its name from its distinctive edge-on silhouette genuinely resembling a classic Mexican sombrero. This galaxy spans approximately 50,000 light-years, slightly smaller than our Milky Way yet possessing extraordinarily beautiful and symmetrical architecture. Its most striking feature remains the brilliant central bulge, like a radiant diamond adorning a hat's crown. This bulge harbors hundreds of billions of ancient stars, predominantly red and yellow, indicating they've transcended youth to enter stable middle age. These stellar veterans average 10 billion years old, nearly as ancient as the universe itself. Encircling this luminous core runs a broad dust lane, resembling elegant hat brim ornamentation. This dust lane actually represents the galaxy's disk, though our edge-on perspective makes it appear linear. Within this dusty band lie vast quantities of gas, dust, and forming young stars. Observing galaxies edge-on allows appreciation of typically hidden structural beauty. Face-on galactic views reveal spiral arms and stellar distribution, while side perspectives clarify vertical architecture, disk thickness, bulge dimensions, and stellar halo extent. The Sombrero Galaxy possesses a surprising characteristic: an unusually abundant globular cluster population. Typical galaxies host several hundred globular clusters, while the Sombrero Galaxy boasts approximately 2,000. These globular clusters encircle the galaxy like pearl necklaces, each containing hundreds of thousands of ancient stars. The galaxy's center conceals a supermassive black hole weighing roughly 1 billion solar masses. Though invisible directly, we infer its presence through surrounding stellar motion. These stars orbit the invisible center at tremendous velocities, like water spiraling around a whirlpool's heart. 65 million light-years distant in deep space, a mysterious galaxy has left astronomers utterly perplexed. NGC 1052 DF2 resembles a cosmic phantom, so sparse and transparent that background galaxies show clearly through it, like viewing scenery through gossamer. This discovery revolutionized astronomical understanding, challenging fundamental concepts of galactic formation and structure. Standard cosmological models predict all galaxies should embed within massive dark matter halos. Though dark matter remains invisible and intangible, its gravitational effects prove crucial for galactic formation and structural maintenance. Without dark matter, galaxies shouldn't form or remain stable. Yet NGC 1052 DF2 apparently defies this rule. This galaxy's total mass consists almost entirely of visible stars, containing minimal dark matter, possibly none whatsoever. It's like discovering a shadowless person or witnessing dance without musical accompaniment. Bewildering and paradoxical. This galaxy's structure also proves exceptional. Though classified as elliptical, unlike typical elliptical galaxies, its stellar density remains extremely low with highly dispersed distribution. The entire galaxy resembles a tenuous starlight mist diffused across vast space. Inhabitants of such a galaxy would experience exceptionally empty night skies, with stellar separations far exceeding our familiar celestial landscape. Scientists propose several theories explaining this anomalous phenomenon. One possibility suggests this galaxy once possessed normal dark matter content, later stripped away through violent astrophysical processes, perhaps galactic interactions or tidal stripping by massive galaxy clusters. Another theory proposes formation within an exceptionally unusual cosmic environment where dark matter density remained inherently low. Some researchers believe NGC 1052 DF2's discovery might support alternative gravity theories attempting to explain galactic behavior without invoking dark matter. If these theories prove correct, galaxies can indeed exist under certain conditions without additional dark matter. Regardless of ultimate truth, NGC 1052 DF2 serves as an invaluable natural laboratory. By studying this unique galaxy, scientists can better understand dark matter's nature and its role in cosmic structure formation. It reminds us that the universe consistently proves more complex and enigmatic than our imagination. 300 million light-years away, a spectacular galactic congregation unfolds. The Coma Cluster resembles a cosmic metropolis where over 1,000 galaxies bind together gravitationally, forming an immense celestial community. This cluster scale proves astounding, containing several dozen times more galaxies than our local group. The Coma Cluster derives its name from its location toward the constellation Coma Berenices. It ranks among Earth's nearest major galaxy clusters and serves as a crucial subject for astronomers studying cluster physics. Its total mass approximates 1 million Milky Way equivalents, with most mass originating from enigmatic dark matter. Within this cluster, we observe diverse galactic types: colossal elliptical galaxies standing like cosmic skyscrapers, magnificent spiral galaxies rotating like celestial pinwheels, and various irregular galaxies with unique morphologies, each harboring individual stories. Most fascinating are thousands of globular clusters floating freely throughout this cluster space. These objects, termed intracluster globular clusters, belong not to specific galaxies but to the entire cluster. Like urban street performers, they wander between galaxies, witnessing large-scale cosmic structural evolution. These intracluster globular clusters likely have multiple origins. Some may have been stripped during galactic interactions, like coastal rocks torn away by tidal forces. Others might represent primordial objects existing since early cluster formation stages. Still others could have formed during galactic collisions, products of cosmic violence. The Coma Cluster holds historical significance as one of humanity's first dark matter detection sites. As early as 1933, Swiss astronomer Fritz Zwicky, studying this cluster, discovered galactic velocities far exceeding what visible matter's gravity could explain. He concluded invisible, missing mass must exist to maintain cluster stability, what we now term dark matter. Modern observations confirm Zwicky's prophetic insight. X-ray observations reveal hot gas distribution within the cluster. Gravitational lensing effects allow us to see dark matter's gravitational influence. These observational results indicate approximately 85% of the Coma cluster's mass derives from dark matter, with only 15% representing directly observable ordinary matter. Over 9 billion light-years away in deep space, a solitary star emits faint yet persistent luminescence. Once called Icarus after the mythological Greek youth who dared fly toward the sun. Though mythological Icarus ultimately fell from flying too high, this cosmic Icarus successfully transmitted its radiance to our instruments. Icarus resides within galaxy cluster max J1149 plus 2223, which itself functions as a gravitational lens. When background starlight passes through this massive cluster, the cluster's gravitational field bends light paths like a colossal magnifying glass, revealing otherwise completely invisible distant objects. This star's light has completed such a tremendous journey that upon reaching our telescopes, it displays the universe at only 30% its current age. During that epoch, the cosmos remained young, with the first galactic generation just beginning formation, and the entire universe appearing utterly different from today. Like receiving a postcard from antiquity with a blurred postmark yet still conveying stories from that distant era. Icarus likely represents a supergiant star possibly tens of times more massive than our Sun. Such stars burn with extraordinary brilliance yet possess relatively brief lifespans of only a few million years. Considering we observe its state from over 9 billion years ago, this star most likely no longer exists, probably having perished long ago in a spectacular supernova explosion. Icarus's discovery process itself constitutes a scientific miracle. While analyzing Hubble Space Telescope data, astronomers noticed a bright point within a distant galaxy image that suddenly appeared then gradually faded. Further analysis revealed this wasn't an intragalactic event, but rather a background star magnified by gravitational lensing. When a cluster star moved into precisely the right position, it enhanced the lensing effect, temporarily brightening Icarus's luminescence. This discovery pioneered a revolutionary research field, observing distant individual stars through gravitational lensing. Previously, astronomers could only observe distant galaxies without resolving constituent stars. Yet gravitational lensing provides a natural supertelescope, allowing glimpses into early universe stellar properties. At an even more remote 12.9 billion light-years, a star called Earendel twinkles with ancient radiance in cosmic depths. This name derives from Tolkien's mythology, symbolizing a luminous messenger bearing bright jewels across the heavens. In Tolkien's legendarium, Earendel represents a half-elf mariner sailing across the sky with a Silmaril-bearing vessel, becoming the brightest star. WHL 0137 LS, our real-world Earendel, dwells within the Sunrise Arc galaxy cluster. Its discovery unfolded with considerable drama and serendipity. In 2022, while using Hubble to observe this galaxy cluster, astronomers noticed an unusually luminous point source. Initially assuming this might represent a distant quasar or transient object, further analysis revealed it as an extraordinarily distant star. This star's dimensions prove astounding, with estimated mass ranging 50 to 100 times solar mass, qualifying it as a genuine supergiant. Its surface temperature reaches 20,000 Kelvin, nearly quadruple our Sun's surface temperature, generating intense blue-white radiance. Observed up close, this star would appear tens of thousands of times brighter than our Sun, capable of illuminating surrounding regions across several light-years. Even more thrilling, Earendel likely represents a population 3 star. Population 3 stars constitute the universe's earliest stellar generation, composed almost entirely of hydrogen and helium with extremely low heavy element content. This occurs because the early universe lacked sufficient supernova explosions to produce and distribute heavy elements. These primordial stars served as cosmic pioneers. Their existence and demise laid foundations for subsequent stellar and planetary formation. Should Earendel indeed prove to be population 3, its discovery would carry immense scientific significance. Population 3 stars have long remained theoretical predictions, with scientists searching extensively for evidence of these primordial stars. Due to their brief lifespans of mere millions of years and existence during the early universe, they're extraordinarily difficult to observe. Earendel might represent our first observed population 3-star, helping verify theoretical models about the early universe and stellar formation. Earendel's light has journeyed through the universe for 12.9 billion years, showing us the cosmos merely hundreds of millions of years post-birth. During that epoch, the universe's first galaxies had just begun forming, cosmic reionization was underway, and the entire cosmos transitioned from darkness toward illumination. However, due to cosmic expansion, Earendel's current actual distance reaches 28 billion light-years. This star most likely no longer exists, probably having perished in a supernova explosion billions of years ago. Yet its light continues propagating through the universe, delivering precious information about cosmic childhood. At the observable universe's very edge, a mysterious object designated HD-1 quietly emits faint crimson luminescence. This object lies 13.5 billion light-years distant, representing one of the most remote and ancient cosmic structures observable. HD-1's discovery represents a major achievement in modern astronomy. It emerged through comprehensive analysis of multiple deep sky survey data, including observations from Subaru Telescope, Vista Telescope, UK Infrared Telescope, and others. Scientists needed to identify this special object among tens of thousands of distant galaxies, a process like finding a specific sand grain on an infinite beach. This object earned designation HD-1 as candidate number 1 in the Hubble Frontier Deep Field Survey. Though the name sounds simple, it represents a milestone in humanity's exploration of cosmic frontiers. HD-1's most remarkable feature remains its unusually brilliant ultraviolet emission. During that distant epoch, the universe lacked sufficient heavy elements to form today's complex objects. Yet HD-1's luminosity exceeds theoretical expectations. This suggests it might represent a starburst galaxy frantically producing stars at rates potentially tens or hundreds of times higher than contemporary typical galaxies. Another possibility involves HD-1 containing some of the universe's earliest supermassive stars, population 3 stars. These primordial giants might possess masses reaching hundreds of solar masses, burning with extraordinary intensity and emitting light millions of times brighter than ordinary stars. If HD-1 indeed harbors such stars, it resembles cosmic dawn's first ray, illuminating the originally dark universe. An even more exciting possibility, HD-1 might contain the universe's most ancient black holes. In the early universe, the first supermassive stars might have collapsed directly into black holes upon fuel exhaustion. These primordial black holes began devouring surrounding material, forming the earliest quasars. If HD-1 represents such an early quasar, it stands among the universe's most ancient monsters. HD-1's redshift value reaches 13.27, meaning we observe it merely 330 million years post-Big Bang. During that era, the universe remained in the reionization epoch, with the first stars and galaxies forming, their intense radiation ionizing cosmic hydrogen gas, enabling the universe's transition from opacity to transparency. Though HD-1 appears as merely a faint crimson speck in our observations, 14 billion times dimmer than the faintest naked-eye stars, it carries crucial information about cosmic origins. By studying distant objects like HD-1, we understand how the universe evolved from post-Big Bang simplicity into today's complex and diverse cosmos. Beyond Neptune's orbit in profound space, a mysterious and magnificent ice kingdom quietly encircles our solar system. This is the Kuiper Belt, a cosmic garland composed of countless frozen objects, resembling an exquisite ancient necklace adorning our solar system. This icy realm story begins 4.6 billion years ago. Then, our solar system existed as a massive rotating disk of gas and dust, the solar nebula. Throughout this primordial disk's different regions, temperatures and conditions varied dramatically. In inner regions near the Sun, temperatures remained too elevated for only rock and metal to condense into solids. In distant outer regions, temperatures allowed water, methane, ammonia, and other substances to freeze. The Kuiper Belt occupies this frigid outer zone, 30 to 50 astronomical units from our Sun. Here, various frozen materials coalesced into objects ranging from kilometer-wide ice chunks to hundreds of kilometers across dwarf planets. These icy worlds function like temporal capsules, perfectly preserving primordial memories from our solar system's genesis. To comprehend the Kuiper Belt's magnitude, envision a cosmic expedition. Beginning from the Sun, we traverse rocky planets Mercury, Venus, Earth, and Mars, cross the asteroid belt between Mars and Jupiter, continue past gas giants Jupiter, Saturn, Uranus, and Neptune, finally reaching the Kuiper Belt's threshold. This journey spans 30 astronomical units. 1 astronomical unit equals the Earth-Sun distance, approximately 150 million kilometers. Upon reaching the Kuiper Belt, we'd stand 4.5 billion kilometers from our Sun. At such distance, the Sun appears merely as a brilliant point providing negligible warmth. The Kuiper Belt's configuration resembles a colossal torus, relatively thin, primarily distributed near the ecliptic plane. Yet this donut scale proves astounding. Inner diameter approximately 6 billion kilometers, outer diameter roughly 7.5 billion kilometers. The entire Kuiper Belt contains hundreds of thousands of objects exceeding 100 kilometers diameter, plus over 1 trillion smaller bodies. Among these icy residents dwell particularly renowned inhabitants. Pluto formerly served as our solar system's 9th planet until reclassification as a dwarf planet in 2006. Besides Pluto, dwarf planets like Eris, Haumea, and Makemake each possess unique characteristics and histories. Deep within this ice kingdom resides a special inhabitant, Pluto. This former 9th planet, now tenderly classified as a dwarf planet, displays a heart-melting feature. An enormous heart-shaped region, like a loving mark left by the universe on this diminutive world. Pluto's discovery itself reads like legend. In 1930, 24-year-old astronomer Clyde Tombaugh, working at Lowell Observatory, identified a moving light point by comparing sky photographs taken on different dates. This discovery thrilled the entire world, with Pluto becoming our solar system's 9th member. However, Pluto's true nature remained veiled until 2015. NASA's New Horizons probe, following a 9.5-year odyssey, finally reached Pluto, transmitting the first clear images of this distant world. When these photographs reached Earth, global audiences were astounded. Pluto proved far more beautiful and complex than anyone imagined. That famous heart-shaped feature received designation Tombaugh Regio, honoring Pluto's discoverer. This heart-shaped region actually comprises 2 distinct geological units. The western portion represents a massive nitrogen ice plain named Sputnik Planitia, commemorating humanity's first artificial satellite. This plain stretches 1,000 kilometers and plunges 4 kilometers deep, the solar system's largest known glacier. Picture this nitrogen ice plain covering an area equivalent to Texas and New Mexico combined, yet composed not of water ice but solid nitrogen. At Pluto's extremely low temperatures around -230 degrees Celsius, nitrogen gas condenses into solid form, creating this massive plain. This plain's surface appears relatively youthful, lacking numerous impact craters, indicating ongoing geological activity. The heart's eastern half consists of different materials, primarily nitrogen ice that evaporated from Sputnik Planitia then recondensed. This material migration process continues between Pluto's poles and equator, resembling Earth's water cycle except involving nitrogen circulation. New Horizons revelations completely transformed our understanding of Pluto. This distant world possesses a complex atmosphere. Though exceedingly thin, it demonstrably exists. It experiences weather variations, including nitrogen snow and methane fog. Pluto's surface terrain exhibits extraordinary diversity: plains, mountains, canyons, and possibly even dunes. Most surprisingly, Pluto might harbor a subsurface ocean. Despite extremely low surface temperatures, internal radioactive decay might provide sufficient heat to maintain liquid water. If this speculation proves accurate, Pluto could represent another potential life habitat, though this possibility remains small. Regarding Pluto's heart-shaped feature formation, scientists propose various theories. Initial concepts suggested connections to internal oceans, but recent research indicates it more likely resulted from an ancient low-velocity impact. This impact struck Pluto obliquely, much like a water balloon hitting ground at shallow angles creates elliptical splash patterns, leaving a heart-shaped impression on Pluto's surface. This impact theory explains both the heart-shaped feature's morphology and other Plutonian characteristics, including rotational axis tilt and certain geological structures. If correct, Pluto's heart commemorates an ancient cosmic event, witnessing our solar system's turbulent early history. Pluto doesn't exist in isolation. It maintains a faithful companion, Charon. This satellite's name derives from Greek mythology's underworld ferryman, responsible for transporting souls across the river Styx. In reality, Charon's relationship with Pluto resembles an eternal duet between cosmic dancers. Charon's discovery carries a heartwarming story. In 1978, astronomer James Christie, examining Pluto photographs, noticed the planet's image appeared somewhat blurred, as if something adhered to it. Further observations confirmed this attachment was actually a satellite. Christie named this satellite Charon, partly honoring his wife Charlene, since Charon's pronunciation resembles Charlene's initial syllables. Charon's dimensions prove impressive. Its diameter approaches 1,200 kilometers, nearly half Pluto's diameter. This size ratio remains unique within our solar system. Most planetary satellites appear much smaller than their parent planets, yet Charon and Pluto's similar sizes lead many astronomers to consider them a binary planet system rather than planet-satellite arrangement. The choreography between Pluto and Charon represents a special celestial mechanical phenomenon called tidal locking. This means Charon's orbital period around Pluto exactly matches Pluto's rotation period, both lasting 6.4 Earth days. Consequently, Charon perpetually faces Pluto with the same hemisphere, while Pluto always presents the same face to Charon. Standing at the correct Plutonian location, Charon would hover permanently at the same sky position, neither rising nor setting. New Horizons unveiled Charon's beauty and complexity. This satellite's surface teems with impact craters, canyons, and enigmatic dark regions. Its most striking feature remains a massive canyon system extending from north to south pole, reaching depths of 9 kilometers. This canyon system, designated Ithaca Chasma, indicates Charon once experienced violent geological activity. Charon's North Polar region bears coverage by a mysterious dark area informally named Mordor, borrowing from Tolkien's literary geography. This dark material's exact nature remains puzzling, though scientists suspect it might represent methane escaped from Pluto's atmosphere, deposited at Charon's North Pole and chemically altered by solar radiation. Charon's other surface features prove equally intriguing. Across its equatorial region stretches a massive tectonic belt resembling an ancient scar, narrating days when this icy world possibly possessed a liquid water ocean. Scientists believe Charon might have harbored a subsurface ocean during early formation, but over time, this ocean gradually froze, causing surface tectonic deformation. The Pluto-Charon system's formation also represents a fascinating topic. The currently most accepted theory involves the giant impact hypothesis, similar to Earth-Moon system formation models. According to this theory, during the early solar system, a large object impacted primordial Pluto, with collision debris eventually coalescing to form Charon. This violent origin contrasts intriguingly with their current graceful duet. Deep within the Kuiper Belt, 1.5 billion kilometers from Pluto, a small yet peculiar object quietly drifts. This is Arrokoth, a snowman-shaped diminutive world that helped solve crucial planetary formation puzzles. Arrokoth's original designation 2014 MU69 represents an unpoetic name indicating discovery year and sequence. Later, the New Horizons team selected a more beautiful name, Arrokoth, meaning sky, in Native American Powhatan language. This name proves both beautiful and reflective of humanity's eternal desire to explore unknown heavens. Arrokoth represents the most distant object ever visited by human spacecraft. On January 1, 2019, 3.5 years after completing the Pluto flyby mission, New Horizons conducted a historic encounter with Arrokoth. This flyby occurred 6.5 billion kilometers from Earth, requiring over 6 hours for signal transmission. When New Horizons images reached Earth, scientists witnessed an unprecedented bizarre morphology. Arrokoth resembled two spheres tenderly connected, forming a flattened snowman configuration. This structure, termed a contact binary in astronomy, indicates two originally independent objects that eventually touched and adhered. This cosmic snowman's dimensions remain relatively modest, approximately 35 kilometers long, 20 kilometers wide, and 10 kilometers thick. Despite its small size, its scientific value proves enormous. Arrokoth provides a rare opportunity to study primordial material from solar system formation's earliest stages. The larger lobe bears designation Ultima Thule, the smaller Thule. These names derive from ancient geographical concepts representing the known world's edges. This naming proves appropriate since Arrokoth truly occupies our solar system's known region's periphery. Arrokoth's surface characteristics also prove fascinating. The entire object displays uniform reddish-brown coloration resulting from organic compounds subjected to prolonged solar radiation. Its surface appears relatively smooth without obvious impact craters, suggesting the Kuiper Belt environment remains relatively tranquil with rare large impact events. Most crucially, Arrokoth resolved a long-standing scientific enigma. How do planets form? Before Arrokoth's discovery, two primary planetary formation theories competed. First, hierarchical accretion theory suggested small objects gradually accumulate into larger bodies through high-velocity collisions. Second, local cloud collapse theory proposed nearby objects slowly gather under gravitational influence. Arrokoth's morphological characteristics provided definitive answers to this controversy. Its smooth surface and two lobes' seamless joining indicate these objects merged at remarkably low velocity, resembling two dancers' tender embrace. High-speed collision formation should have left more destructive scarring. This discovery carries profound implications. It reveals that at least in our solar system's outer regions, planetary formation represents a gentle process rather than violent collision. This gentle accretion model applies not only to small objects but might also constitute an important mechanism for large planet formation like Earth. New Horizons Project scientist Alan Stern noted, "The evidence is so compelling that we have definitively resolved a decades-long controversy about planetary embryo formation. This diminutive cosmic snowman answered fundamental questions about solar system origins." Beyond Pluto and Arrokoth, the Kuiper Belt harbors many other intriguing residents, each possessing unique stories and characteristics. Eris ranks among the Kuiper Belt's largest known objects, its discovery directly precipitating Pluto's reclassification as a dwarf planet. Eris's diameter approximates 2,300 kilometers, slightly exceeding Pluto's, with mass roughly 27% greater. Named after the Greek discord goddess, this designation proves apt since its discovery indeed sparked discord within astronomical circles, fierce debate about planetary definitions. Eris possesses a small satellite named Dysnomia after Eris's daughter, meaning lawlessness. This satellite's discovery enabled scientists to calculate Eris's mass, thereby confirming its greater weight than Pluto. Haumea represents another fascinating dwarf planet. Its morphology proves extraordinarily distinctive, appearing elliptical with a long axis around 2,000 kilometers and short axis approximately 1,000 kilometers, resembling a gigantic football. This peculiar shape results from its extremely rapid rotation. Haumea completes one rotation every 4 hours, among the solar system's fastest known rotation rates. Haumea also possesses its own ring system, exceptionally rare among dwarf planets. In 2017, astronomers discovered this ring through observing Haumea's stellar occultation. Haumea's name derives from Hawaiian fertility goddess, reflecting its characteristic of having two satellites, like a mother with children. Makemake bears the name of Easter Island mythology's creation deity. It represents the Kuiper Belt's second brightest object after Pluto, though not until 2016 was its small satellite discovered. Makemake's surface bears methane and nitrogen ice coating, providing relatively high albedo. Sedna remains a highly mysterious object with an extremely elliptical orbit, its aphelion approximately 900 astronomical units from the Sun, perihelion still 76 astronomical units. Sedna's orbital period spans 11,400 years, meaning since human civilization's dawn, it has completed less than one full orbital cycle. Sedna's existence hints at additional unknown objects in our solar system's outer reaches. The Kuiper Belt serves not only as home to various icy objects but also as birthplace for numerous short-period comets. These comets function like messengers from the Ice Kingdom, regularly visiting the inner solar system while providing spectacular celestial shows for Earth's inhabitants. When Kuiper Belt objects experience gravitational disturbances, such as Neptune's influence or collisions with other bodies, they might alter orbits and begin journeying toward the inner solar system. Once these icy objects approach the Sun, solar heat begins sublimating surface ice, forming coma and tails, transforming them into observable comets. Halley's Comet represents one of the most famous Kuiper Belt origin comets. This comet returns to the inner solar system every 76 years, its orbit extending beyond Neptune's path. Ancient Chinese astronomers recorded Halley's Comet appearances as early as 240 BC, making it among humanity's longest continuously observed comets. Comet Shoemaker-Levy 9 provides another famous example. This comet spectacularly collided with Jupiter in 1994, humanity's first directly observed solar system collision event. This collision's energy equaled 600 trillion tons of TNT, creating giant dark spots in Jupiter's atmosphere persisting for months. Comets might have played crucial roles in Earth's biological evolution. Some scientists theorize that water and organic compounds on early Earth partially originated from cometary impacts. If this theory proves correct, these icy Kuiper Belt residents might represent Earth life's original suppliers. Presently, Earth continues receiving regular impacts from small Kuiper Belt objects. Most impactors remain small, completely incinerating in our atmosphere to create meteors. Occasionally, larger objects survive atmospheric entry, forming meteorites. By studying these Kuiper Belt meteorites, scientists learn about early solar system chemical composition and physical conditions. Beyond the Kuiper Belt lies an even more distant and mysterious region, the Oort cloud. This hypothetical spherical realm presumably surrounds our entire solar system, extending from roughly 2,000 to 100,000 astronomical units. The Oort cloud honors Dutch astronomer Jan Oort, who first proposed this concept in 1950 to explain long-period comet origins. These comets possess orbital periods spanning thousands or tens of thousands of years, originating from our solar system's outermost reaches. Unlike the ring-shaped Kuiper Belt, the Oort cloud appears spherical, resembling a colossal soap bubble enveloping our solar system. This region might contain trillions of icy objects with total mass possibly equivalent to several Earths. Oort cloud objects remain so distant that solar gravity affects them weakly. This renders them susceptible to gravitational disturbances from nearby stars or interstellar gas clouds. When such disturbances occur, some Oort cloud objects might enter highly elliptical orbits, becoming long-period comets. Though we haven't directly observed Oort cloud objects except those already transformed into comets, its existence appears virtually certain. Long-period comets' orbital characteristics and chemical compositions all support the Oort cloud's existence. Comet Hale-Bopp exemplifies Oort cloud origins. This comet became one of the 20th century's most spectacular when reaching peak brightness in 1997. Its orbital period approximates 2,500 years, with its previous inner solar system visit occurring around 2000 BC. Oort cloud objects might preserve primordial solar system formation material and possibly include visitors from other stellar systems. By studying long-period comets, we learn about our solar system's outer environment and early evolutionary history. The Kuiper Belt and Oort cloud represent humanity's final exploration frontiers. Though New Horizons successfully visited Pluto and Arrokoth, countless secrets within this ice kingdom await revelation. Currently, New Horizons continues flying through the Kuiper Belt. Though its primary mission concluded, scientists still seek potential new targets. However, at such remote distances, finding suitable flyby candidates proves extremely challenging, requiring precise orbital calculations and considerable fortune. Future Kuiper Belt missions might include orbital spacecraft capable of long-term study of specific Kuiper Belt objects. Some scientists propose sample return missions, bringing Kuiper Belt's primordial material back to Earth for detailed analysis. Though such missions present extraordinary technical challenges, they would provide invaluable information about solar system origins. The James Webb Space Telescope has also opened new possibilities for Kuiper Belt research. Its powerful infrared observational capabilities can help discover additional Kuiper Belt objects while studying their composition and physical properties. Webb has already begun observing select Kuiper Belt objects, including Pluto and other dwarf planets. In the more distant future, specially designed deep space probes might venture toward the Oort cloud, representing one of human spaceflight history's most ambitious undertakings. Such probes would require decades or centuries to reach their destinations, yet would provide first-hand data about our solar system's outermost environment. In 1977, two diminutive yet courageous explorers embarked upon humanity's longest and most solitary journey. Voyager 1 and Voyager 2 resemble cosmic fireflies, carrying human curiosity, dreams, and yearning for the unknown as they slowly journey toward distant interstellar space. These two probes' story begins with a rare celestial mechanical opportunity. Every 176 years, our solar system's four giant planets, Jupiter, Saturn, Uranus, and Neptune, align in a special configuration termed the Grand Tour alignment. The previous such alignment occurred during Napoleon's European dominance. The next won't happen until the 22nd century. NASA engineers recognized this once-in-a-lifetime opportunity could enable a single spacecraft to visit all four giant planets sequentially, utilizing each planet's gravity for acceleration and trajectory modification, like a billiard player using table edges to redirect ball paths. This technique became known as the gravity slingshot effect, or gravity assist. The original plan, called the Grand Tour, represented an ambitious project designed to launch multiple probes for comprehensive outer solar system exploration. Budget constraints simplified this grand vision into launching two relatively simple yet powerful probes. Voyager probe design embodied wisdom and foresight. They carried radioisotope thermoelectric generators, devices converting heat from plutonium-238 radioactive decay into electricity. Selecting this power source over solar panels proved essential since beyond Jupiter's orbit, sunlight becomes too feeble to provide adequate power. These nuclear hearts generated 157 watts at launch. Though power gradually diminishes over time, having every 87.7 years, it sufficed for decades of operation. This long-term power capability established foundations for subsequent interstellar missions. Each Voyager resembles a precision technological symphony orchestra comprising 11 scientific instruments. These instruments include cameras, magnetometers, plasma detectors, cosmic ray detectors, and others capable of studying planetary atmospheres, magnetic fields, radiation environments, plus their satellites and ring systems. To ensure mission success, engineers designed backup components for critical systems. This redundancy proved extraordinarily wise. 37 years later, when Voyager 2's main thruster system failed, backup thrusters, dormant for decades, activated perfectly, allowing mission continuation. Voyager probes also carried special passengers, golden records. These two 12-inch gold-plated copper discs contain samples of Earth's life and culture. Music, natural sounds, multilingual greetings, and encoded images. These records resemble messages in bottles. If discovered by extraterrestrial civilizations, they would learn of humanity's existence and our cosmic love. Voyager probe's first destination was our solar system's largest planet, Jupiter. This gas giant's mass exceeds all other planets combined. It functions like the solar system's cosmic vacuum cleaner, using powerful gravity to shield the inner solar system from asteroid and comet impacts. When Voyager 1 approached Jupiter in March 1979, the scene surpassed all expectations. Jupiter's atmosphere resembles a never-ending abstract masterpiece, brimming with swirls, storms, and vibrant bands. These bands form from cloud layers at different altitudes, their colors originating from various chemicals. Ammonia's white, phosphorus's red, sulfur's yellow. Jupiter's most renowned feature remains the Great Red Spot, a massive anticyclonic storm persisting for at least 350 years. This tempest's diameter exceeds Earth's entire circumference, with wind speeds reaching 400 kilometers per hour. Voyager observations revealed the Great Red Spot resembles Jupiter's colossal eye, serenely observing space while witnessing solar system transformations. Near the Great Red Spot, Voyager discovered numerous other storm systems, including white oval tempests and smaller cyclones. These storms interact dynamically, sometimes merging, sometimes splitting, creating Jupiter's complex atmospheric choreography. One of Voyager's major discoveries established that Jupiter possesses a ring system. Previously, only Saturn was known to have rings. Jupiter's rings appear dark and tenuous, primarily composed of dust particles, making terrestrial observation extremely difficult. These rings likely formed from debris created when small satellites or asteroids impacted Jupiter's inner moons. However, Jupiter's most astounding discoveries emerged from its satellite system. Voyager revealed Jupiter's 4 largest moons: Io, Europa, Ganymede, and Callisto, each representing a unique world. Io ranks as the solar system's most geologically active body. Voyager captured volcanic eruptions on Io's surface, with ejecta reaching 300-kilometer heights. These volcanoes don't spew magma but rather sulfur and sulfides. Io's volcanic activity results from tidal forces exerted by Jupiter and other large satellites, continuously stretching and compressing Io's interior, generating frictional heat. Europa appears as an ice-shrouded world, its surface etched with enigmatic fractures and ridges. Voyager imagery suggested that beneath this icy shell might lie a liquid water ocean. If the speculation proves accurate, Europa could represent one of our solar system's most promising locales for discovering life. Ganymede represents our solar system's largest moon, even exceeding Mercury's dimensions. It possesses its own magnetic field, indicating a molten core. Callisto appears as an ancient world, its surface scarred with impact craters recording our solar system's violent early bombardment history. Voyager 2 reached Jupiter 4 months later, providing additional observational data and imagery. These coordinated observations granted scientists unprecedented understanding of the Jovian system. After departing Jupiter, both Voyager probes continued outward, targeting magnificent Saturn. If Jupiter serves as our solar system's monarch, then Saturn reigns as its most elegant queen, crowned with breathtaking rings. When Voyager 1 approached Saturn in November 1980, it unveiled a ring system far more complex and beautiful than imagined. From Earth, Saturn's rings appear as several simple continuous bands, yet Voyager's close observations revealed these rings actually comprise hundreds of delicate ringlets, resembling dense grooves on a cosmic phonograph record. Saturn's rings consist primarily of water ice particles ranging from tiny crystals to house-sized chunks. These ice particles sparkle under sunlight, creating one of our solar system's most breathtaking spectacles. The ring's total thickness measures merely tens of meters, yet their diameter exceeds 270,000 kilometers, equivalent to 2/3 the Earth-Moon distance. Voyager discovered numerous novel features within Saturn's ring system. The F-ring proved most perplexing, twisted into braided patterns while constantly shifting configuration. This intricate structure results from gravitational effects of 2 small satellites, Prometheus and Pandora. These shepherd satellites function like cosmic sheepdogs, using gravity to herd ring particles and prevent their dispersal. Even more mysterious appeared the spokes phenomenon within Saturn's rings. These dark radial structures manifest and vanish like spectral apparitions. These spokes violate fundamental orbital mechanics. Inner particles should orbit faster than outer particles, yet spokes maintain coherent structure. Scientists later discovered electrostatic forces cause this phenomenon. Minute dust particles acquire electrical charge, forming these strange structures under Saturn's magnetic field influence. Saturn's satellite system also brims with surprises. Titan represents Saturn's largest moon and our solar system's second largest satellite. Voyager discovered Titan possesses a dense atmosphere primarily composed of nitrogen, making it the only satellite besides Earth with substantial atmospheric envelope. Titan's atmosphere proves so thick it completely obscures the surface like an orange shroud. Enceladus provided another astounding discovery. This diminutive satellite ejects massive water vapor plumes from its south polar region, ascending thousands of kilometers. These plumes not only indicate internal liquid water, but also suggest potentially life-suitable environments. Water vapor expelled by Enceladus supplies Saturn's E-ring, creating an elegant cosmic cycle. Voyager also revealed Saturn gradually loses its rings. Ring particles slowly spiral into Saturn's atmosphere under gravity, creating ring rain. According to calculations, Saturn's rings might completely disappear within 300 million years, merely an instant on cosmic timescales. After completing Saturn exploration, only Voyager 2 continued outward since Voyager 1 chose a trajectory past Titan, altering its flight path and preventing continued visits to Uranus and Neptune. Voyager 2 became humanity's solitary pioneer exploring the outer solar system. In January 1986, Voyager 2 reached enigmatic Uranus. This planet resembles an intoxicated dancer, tumbling through space with an extreme 98-degree axial tilt. This unique inclination means Uranus's polar regions alternately face the Sun, with each pole's summer lasting 42 Earth years and winter equally long. Uranus displays a beautiful blue-green hue resulting from atmospheric methane. Unlike Jupiter and Saturn's dynamic atmospheres, Uranus exhibits unusually placid appearance with virtually no visible cloud features. This serene exterior masks internal complexity. Voyager 2 discovered a shocking characteristic of Uranus's magnetic field. Its magnetic axis tilts 59 degrees from its rotation axis. On Earth, this angle measures only 12 degrees. This extreme misalignment means when Uranus rotates, its magnetosphere wobbles like an unbalanced gyroscope, creating one of our solar system's most complex magnetic field environments. Uranus also possesses a ring system, though much darker than Saturn's, primarily composed of black organic material. These rings appear extremely narrow, thin as pencil lines, maintained by small satellites' gravitational shepherding. Voyager 2 discovered 2 new ring-shepherd satellites, confirming scientists' theories about narrow ring stabilization mechanisms. Uranus's satellite family resembles an eccentric clan. Before Voyager 2's visit, Uranus had 5 known satellites, all named after Shakespearean characters: Ariel, Umbriel, Titania, Oberon, and Miranda. Voyager 2 discovered 11 additional satellites, substantially enriching this family. Miranda provided the most astonishing discovery. This small satellite's surface appears like a shattered puzzle reassembled, displaying extraordinarily complex geological history. It features massive canyons plunging 20 kilometers deep, plus bizarre terrace terrain and V-shaped structures. Some scientists theorize Miranda might have been completely fragmented by enormous impact, then reassembled under gravitational influence. Discoveries within the Uranus system challenged numerous theories about planetary formation and evolution. Its extreme tilt, unique magnetic field structure, and diverse satellite system all indicate Uranus possesses a dramatically different history from other giant planets. In August 1989, 12 years post-launch, Voyager 2 finally reached its final planetary destination, Neptune. This gorgeous deep blue planet occupies our solar system's periphery, approximately 4.5 billion kilometers from the Sun, receiving merely 1,000th Earth's solar illumination. Despite such solar remoteness, Neptune exhibits surprising dynamism. It hosts our solar system's most powerful winds, with velocities reaching 2,100 kilometers per hour, approaching sonic speeds. This extreme wind velocity remains enigmatic since Neptune receives insufficient solar energy to drive such violent atmospheric motion. Neptune's deep blue saturation exceeds Uranus's, also attributable to atmospheric methane. Yet Neptune's atmosphere apparently contains unknown components, making it bluer than Uranus. This mystery persists. Voyager 2 discovered a colossal storm system on Neptune, the Great Dark Spot. This elliptical tempest approximates Earth's size, rotating counterclockwise at 2,400 kilometers per hour. Remarkably, when Hubble Space Telescope observed Neptune years later, the Great Dark Spot had vanished, though a new dark spot appeared elsewhere. This indicates Neptune's atmosphere changes extraordinarily rapidly, far more dynamic than Jupiter's Great Red Spot. Neptune's magnetic field also proves peculiar, with magnetic and rotation axes separated by 47 degrees. Though less extreme than Uranus, still highly unusual. More puzzling, neither Neptune nor Uranus generates magnetic fields from planetary centers, but from intermediate layers. Neptune's ring system appears dark and sparse, composed of several incomplete arc segments. These ring arcs bear names Liberty, Equality, Fraternity, commemorating the French Revolution. These incomplete ring structures prove difficult to maintain. Their existence likely relates to gravitational disturbances from nearby small satellites. Neptune's largest satellite, Triton, ranks among our solar system's coldest objects, with surface temperatures merely -235 degrees Celsius. Yet, on this frigid world, Voyager 2 discovered geyser activity. These nitrogen geysers propel dark material to 8-kilometer heights. Then atmospheric winds blow it laterally, creating dark surface streaks. Triton follows a retrograde orbit, moving opposite to Neptune's rotation. This strongly suggests Triton originally represented a captured Kuiper Belt object. If this theory proves correct, Triton becomes our first close-up Kuiper Belt object observation, preceding New Horizons' Pluto visit by 26 years. After completing Neptune's flyby, Voyager 2 officially concluded its planetary exploration mission. Both Voyager probes now flew toward our solar system's outer reaches, beginning their more solitary yet equally important interstellar mission. Before entering interstellar space, Voyager 1 captured a photograph of profound philosophical significance for humanity. On February 14, 1990, at Carl Sagan's suggestion, Voyager 1 directed its camera toward Earth, capturing the famous pale blue image from 6 billion kilometers away. In this photograph, Earth appears as merely a tiny azure speck suspended in sunlight, occupying less than 1 pixel. Sagan's description of this image became one of humanity's most beautiful literary achievements. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. This photograph reminds us of Earth's fragility and preciousness. Within the vast cosmos, our home represents merely a dust speck, yet it remains the only place we know harboring life. This realization proves both humbling and inspires greater appreciation for our shared planetary home. After photographing the pale blue dot, both Voyagers continued toward our solar system's edge. They needed to cross several crucial boundaries before reaching genuine interstellar space. The first boundary is the termination shock. Here, solar wind decelerates from supersonic to subsonic velocities as it begins experiencing pressure from the interstellar medium. Voyager 1 crossed this threshold in December 2004. Voyager 2 reached this boundary in August 2007. Beyond the termination shock lies the heliosheath, a turbulent region where decelerated solar wind accumulates and heats. This region contains unexpected complexity. Voyager discovered the heliosheath isn't smooth and uniform as theoretical predictions suggested, but filled with magnetic field bubbles and intricate structures. The final boundary is the heliopause, where solar wind completely ceases and interstellar medium begins dominating. On August 25, 2012, Voyager 1 historically crossed this boundary, becoming the first human-made object entering interstellar space. 6 years later, November 5, 2018, Voyager 2 also crossed the heliopause. Surprisingly, both probes crossed the heliopause at virtually identical distances, approximately 120 astronomical units, despite their crossings being separated by 6 years and occurring during different solar activity cycles. This indicates our heliosphere's size remains more stable than previously anticipated. Upon entering interstellar space, Voyager probes began exploring a completely different environment. Here, without solar wind protection, cosmic ray intensity dramatically increases. Plasma density also greatly exceeds heliospheric levels, approximately 40 times higher. Interstellar space is an empty void but contains sparse gas, dust, and magnetic fields. These materials primarily represent supernova explosion products from billions of years ago, plus material dispersed from other stars. Voyager probes now directly sample this interstellar material, providing first-hand information. One of the most surprising discoveries involves interstellar magnetic field direction differing from expectations. Scientists originally anticipated that upon entering interstellar space, magnetic field direction would change markedly since it should primarily respond to nearby stellar influences. Yet Voyager measured interstellar magnetic field direction almost identical to that within the heliosphere, suggesting our solar system might reside within a magnetic field region shaped by ancient supernova explosions. As time progresses, Voyager probes begin showing their age. Their power slowly diminishes, with scientific instruments shutting down sequentially to conserve energy. In 2022, Voyager 1 began transmitting garbled telemetry data, concerning engineers for months until finally identifying a computer system malfunction. In 2023, Voyager 2 temporarily lost Earth contact due to a communication error. These malfunctions remind us that these 45-year-old probes have far exceeded their design lifespans. Originally designed for 5-year missions, they've now operated nearly half a century. Every continuing operational day represents a minor miracle. Even when Voyager probes eventually lose Earth contact, their odyssey will continue. They'll wander our galaxy for billions of years, witnessing stellar birth and death, galactic collisions and mergers. Approximately 40,000 years hence, Voyager 1 will pass within 1.6 light-years of star AC plus 793888 in Camelopardalis. After 296,000 years, Voyager 2 will fly past Sirius at 4.3 light-years distance. These distances appear close on cosmic scales, yet remain unreachably distant for humanity. Should extraterrestrial civilizations eventually discover Voyager probes, they'll find Earth and human information on the golden records. This information includes Earth's location, human appearance, terrestrial life sounds, multilingual greetings, and music spanning Bach to Beethoven to Chuck Berry. Voyager probes embody humanity's most noble qualities: curiosity, courage, and knowledge-seeking passion. They represent our message to the universe, demonstrating that within this vast cosmos, at least one species dares explore the unknown and reach toward the stars. Now, when we gaze upon night skies, we know that in distant interstellar space, two tiny human-made objects sail through the universe representing all humanity. They carry our dreams and aspirations, continuing this endless exploration voyage. When we contemplate stars on tranquil evenings, our hearts invariably stir with ancient and profound questions. How vast is the universe truly? Does it possess boundaries? Or does it extend infinitely? These questions resemble gentle lullabies that have accompanied human contemplation for millennia, still softly resonating in scientists' and philosophers' hearts today. The infinity concept itself brims with poetry and mystery. In mathematics, infinity means no largest number exists. Regardless of what enormous number you name, someone can always name a larger one. Just as numerical ladders never end, the universe might always contain another star, another galaxy awaiting our discovery. Envision what infinite universe truly signifies. It means at infinite distance, there might exist another completely identical you, reading precisely these same words. This isn't science fiction, but mathematical inevitability within infinite universe. In infinite space, all possible arrangements and combinations would repeat, including the exact atomic arrangement constituting you. However, infinity also possesses different magnitudes. This sounds contradictory yet proves mathematically valid. An infinitely long line and an infinitely large plane both represent infinity, yet the plane contains more infinity than the line. Similarly, different universe shapes might contain distinct infinity types. In cosmic geometry, the simplest and most intuitive model involves a flat universe. Envision the universe as an infinitely expansive tender blanket spread across four-dimensional spacetime. In such a universe, Euclidean geometry rules apply perfectly. Parallel lines remain perpetually parallel, triangle interior angles sum to 180 degrees. Circle circumference equals diameter times pi. Within a flat universe, you could travel infinitely far in any direction without ever returning to your starting point. Whenever you believe you've reached some boundary, you'll discover more space awaiting exploration ahead. This resembles wandering through an endless library where finishing one book always reveals more volumes on shelves. This universe model provides comforting regularity. Physical laws remain identical everywhere, with space properties uniform throughout. Conducting an experiment in one cosmic corner and repeating it elsewhere would yield identical results. This consistency provides solid foundations for scientific research. Yet, flat universe also raises profound philosophical questions. If space truly extends infinitely while matter types remain finite, then at sufficiently distant locations, all possible material arrangements would repeat. This means countless U copies exist, some identical, others slightly different. This concept proves both thrilling and bewildering. Flat universe infinity also implies infinite energy and information content. This challenges physics since many physical laws assume finite total system energy. Handling this infinity represents one of modern cosmology's important questions. Alternatively, the universe might be curved like a colossal soap bubble encompassing all existence. In a spherical universe, space itself curves, and though you can't sense this curvature, its effects prove profound. In such a universe, traveling straight in one direction would eventually return you to your starting point, much like surface travel on Earth. This sounds peculiar, but consider an ant crawling on a balloon surface. To the ant, the balloon surface constitutes its entire universe, though this universe appears obviously curved to us. A spherical universe's most fascinating characteristic suggests that theoretically, with a sufficiently powerful telescope, you might observe the back of your own head. This occurs because light travels along curved space, eventually circling the universe to return to its origin. Naturally, due to finite cosmic age, light hasn't had adequate time to complete such a universal circuit, so this scenario won't occur in reality. In spherical universe, parallel lines gradually converge and eventually intersect. Triangle interior angles exceed 180 degrees, with larger triangles showing greater deviation. These geometric properties resemble phenomena we observe on Earth's surface. Drawing a sufficiently large terrestrial triangle yields interior angles exceeding 180 degrees. Spherical universe remains finite yet boundaryless, like Earth's surface possessing finite area, while you never find Earth's surface edges. In such universe, total matter quantity, total energy, and total information all remain finite, providing physics with more elegant frameworks. This universe model also inspires fascinating philosophical contemplations. If the universe proves finite, then its possible information content also remains finite. This means the number of possible different phenomena remains finite. Though this number might prove unimaginably vast, it nonetheless remains finite. The third possibility involves hyperbolic universe, the most challenging to visualize yet perhaps most intriguing geometric form. In such universe, space itself continuously expands, with all parallel lines diverging like petals unfurling when flowers bloom. To understand hyperbolic geometry, consider a saddle's surface. At any saddle point, you can identify two perpendicular directions, one curving upward, one downward. This negative curvature surface represents hyperbolic geometry's two-dimensional analogy. In hyperbolic universe, triangle interior angles sum to less than 180 degrees, with larger triangles showing greater deviation. Through any single point, infinitely many non-intersecting parallel lines can be drawn. These geometric properties differ completely from daily experience yet remain mathematically sound. Hyperbolic universe model appears most consistent with observed reality. We observe every galaxy receding from others. The universe continuously expands. Perhaps this expansion requires no mysterious dark energy explanation but merely represents natural consequences of cosmic geometric shape. In hyperbolic universe, infinity becomes more infinite than any other model. Here space grows exponentially. Exploring new regions reveals more space and possibilities than expected, like opening one door only to find two new doors behind it, with each new door concealing even more doors. This universe model carries important implications for understanding cosmic ultimate fate. In hyperbolic universe, expansion would continue eternally with accelerating velocity. Eventually, intergalactic distances would become so vast that each galaxy would spend its remaining existence in isolated cosmic islands. To truly comprehend cosmic geometry, we must consider how time and space elegantly interweave within Einstein's relativity. Time no longer represents absolute flow but combines with space to form four-dimensional spacetime structure. Envision spacetime as a massive rubber membrane calmly extending across four dimensions. Without matter present, this membrane remains perfectly flat. When massive objects appear, they create spacetime membrane depressions, like heavy balls placed on bedsheets creating indentations. This curvature represents the gravity we experience. We're not pulled toward Earth's center, but naturally moving along spacetime geometry curved by Earth's mass. This represents a poetic concept. Gravity isn't a force, but cosmic geometry's expression. Black holes exemplify extreme spacetime curvature. Within black hole event horizons, spacetime curves so severely that all outward leading paths vanish. Regardless of movement direction, you'd be drawn back toward the black hole's center, like being trapped in a maze where every path leads back to the starting point. Spacetime curvature also explains observable gravitational lensing effects. When distant galactic light passes through foreground massive objects, light follows curved spacetime paths like passing through enormous natural magnifying glasses. This effect not only confirms general relativity predictions but also provides tools for observing more distant universe. Gravitational waves represent another spacetime curvature manifestation. When two black holes or neutron stars spiral toward each other, they generate spacetime ripples like pond waves. These spacetime ripples propagate at light speed. When passing Earth, they cause extremely minute spatial stretching and compression. In 2015, humanity first directly detected gravitational waves, inaugurating gravitational wave astronomy's new era. The universe's true shape will determine our ultimate destiny. This transcends abstract geometric questions, fundamentally concerning the future of all cosmic life and structure. If the universe proves flat, it will expand eternally, though expansion velocity gradually decreases. In this scenario, stars will slowly exhaust fuel, black holes will gradually evaporate through Hawking radiation, and ultimately the universe will achieve heat death, uniform temperature and maximum entropy with no ordered structures existing. If the universe proves spherical, the situation becomes more dramatic. In this geometry, cosmic expansion might gradually decelerate, halt, then reverse into contraction. All galaxies would begin approaching each other, with the universe experiencing a Big Bang opposite process, the Big Crunch. During Big Crunch, all matter and energy would reaggregate, possibly triggering another Big Bang to initiate new cosmic cycles. If the universe proves hyperbolic, expansion would accelerate eternally. In this case, dark energy would drive the universe into a phase called the Big Rip. Eventually, expansion would become so violent that molecules, atoms, and even subatomic particles would be torn apart. Current observational evidence suggests our universe closely approximates flatness, though uncertainty persists. Precise measurements by the European Space Agency's Planck satellite indicate the universe's geometry parameter omega approaches 1, corresponding to flat universe. Yet this precise flatness itself constitutes a mystery. Why would the universe exist so precisely at the critical point between flat and curved? This question leads to cosmic inflation theory. According to this theory, the universe experienced exponential rapid expansion during extremely brief periods after birth. This inflation would flatten any original curvature, like inflating a balloon makes its surface appear increasingly planar. However, inflation theory also introduces new questions. If inflation truly occurred, our observable universe might represent only an infinitesimal portion of a larger structure. Beyond our observable universe might exist countless other universe bubbles, each with distinct physical laws and constants. This forms multiverse theory's foundation. Measuring cosmic geometric shape represents one of modern cosmology's major challenges. Scientists employ various methods to detect spatial curvature, each with unique advantages and limitations. The most direct approach involves measuring large-scale geometric relationships. In flat universe, Distant objects' angular size versus distance relationships follow simple geometric laws. In curved universe, these relationships would deviate. By precisely measuring brightness and angular sizes of distant supernovae, galaxies, and other standard candle objects, scientists can infer spatial geometric properties. Another crucial method analyzes temperature fluctuations within cosmic microwave background radiation. These fluctuations' angular scale distributions contain vital information about cosmic geometry. In flat universe, fluctuation peaks appear at specific angular scales. In curved universe, these peaks shift. Baryon acoustic oscillations provide another powerful probe. During the early universe, baryon matter and photons coupled together, forming sound waves. These sound waves left characteristic scales throughout the universe, now manifesting as periodic features in galactic distribution. By measuring how this characteristic scale changes at different redshifts, scientists can track cosmic expansion history and spatial geometric properties. Gravitational lensing effects also provide cosmic geometry information. Large-scale structures bend light from more distant objects, producing multiple images, arc images, or Einstein rings. These lensing effects' statistical properties reflect matter distribution throughout the universe and spatial geometric properties. Despite possessing numerous observational methods, precisely measuring cosmic geometry remains challenging. Various systematic errors, theoretical uncertainties, and observational noise all influence results. Current observations indicate the universe closely approximates flatness, though we cannot completely eliminate slight curvature possibilities. Cosmic geometric shape transcends mere scientific inquiry. It touches the most profound philosophical questions. If the universe proves infinite, then, in some sense, everything possible will occur. What implications does this hold for free will, moral responsibility, and life's meaning? In infinite universe, countless versions of you exist, making every choice you haven't made. Some versions live superior lives, others inferior. Does this render your choices meaningless? Or conversely, does this make every choice extraordinarily significant since it defines this specific you among infinite possibilities? What if the universe proves finite? Finite universe implies finite information quantity and finite complexity. Does this make life and consciousness more precious as rare products of the universe's finite resources? Cosmic geometry also affects our understanding of science itself. In infinite universe, do scientific laws remain identical everywhere? If space truly proves uniform and isotropic, then physical laws we discover on Earth should apply universally. Yet, if the universe exhibits non-uniformity on larger scales, we might need to reconsider science's universality. These questions lack simple answers, yet they remind us that cosmological research addresses not merely distant objects and abstract mathematics, but our existence's most fundamental questions. When we gaze at starry skies contemplating cosmic shape, we're actually contemplating our place within this vast existence. Like ancient humans gathering around campfires while gazing into endless darkness, modern astronomers use precision telescopes to peer at the observable universe's mysterious edge. What secrets lie concealed beyond that distant boundary? More similar galaxies and stars, or completely different cosmic landscapes? The observable universe's boundary resembles an invisible yet absolute curtain, separating us from broader cosmic reality. This boundary isn't constructed from physical barriers but determined by cosmic expansion's fundamental nature. Beyond that threshold, space expands so rapidly that even light cannot traverse this ever-widening chasm to reach us. Imagine standing on a rapidly moving conveyor belt, attempting to walk toward the opposite end. If the belt moves faster than your walking speed, you can never reach the destination. Similarly, beyond the observable universe's edge, spatial expansion velocity exceeds light speed, making information from there forever unable to reach us. This boundary isn't static but slowly expands over time. Every moment, new spatial regions enter our observable range, like dawn light gradually illuminating more distant horizons. Simultaneously, more remote regions disappear forever from our view due to accelerating expansion. However, in 2008, astronomers noticed a perplexing phenomenon. Hundreds of galaxy clusters appeared to drift slowly in the same direction, resembling collective avian migration. This large-scale, coordinated motion received designation dark flow, its existence suggesting that beyond the observable universe's edge, some massive and mysterious gravitational source might lurk hidden. This discovery resembles suddenly detecting a mysterious undercurrent beneath a seemingly calm lake surface. Superficially, the universe should exhibit uniformity and isotropy on large scales, like thoroughly stirred coffee. Yet dark flow's existence suggests that where we cannot observe, massive non-uniform structures might exist, like concealed boulders creating invisible currents beneath lake surfaces. Imagine witnessing an entire fleet sailing in identical directions. You might deduce a powerful lighthouse or port in that direction beckoning them. Similarly, these galaxy clusters' collective motion might indicate some invisible massive structure exerting influence from the distance. Dark flow's magnitude proves astounding. It involves not merely a few galaxies but large-scale structures spanning billions of light-years. These galaxy clusters move toward Centaurus and Hydra directions at velocities of 600,000 kilometers per second. This speed might not sound impressive, yet for such enormous celestial structures, it represents quite remarkable motion. To study this mysterious phenomenon, scientists turned toward the universe's most ancient light, cosmic microwave background radiation. These photons represent Big Bang afterglow, like warm embers from an ancient campfire still gently radiating throughout the universe today, carrying precious information about cosmic infancy. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, a precision instrument resembling a tender listener, quietly collecting these soft signals from cosmic depths. MAP's mission involved mapping cosmic microwave background radiation in detail, providing fundamental information about cosmic structure, composition, and evolution. This mission's technical challenges proved enormous. Cosmic microwave background radiation temperature measures merely 2.7 degrees above absolute zero, with internal temperature variations even more minute, only 100,000ths of degree differences. Like attempting to measure paper thickness variations where such variations equal 1,000th of atomic dimensions. WMAP operated at Lagrange point L2, 1.5 million kilometers from Earth, for 9 years, accumulating massive datasets. These data not only helped determine cosmic age, composition, and geometric shape, but also provided dark flow research foundations. To understand dark flow's discovery method, we must comprehend a subtle physical effect, the Sunyaev-Zeldovich effect. This effect, named after two Soviet physicists, describes high-energy electrons interacting with cosmic microwave background photons. Envision cosmic microwave background photons as pollen in gentle breezes, while galaxy cluster high-energy electrons resemble bees. When bees encounter pollen, they impart additional energy, slightly elevating temperature. This interaction proves negligible at individual photon levels. Yet when involving entire galaxy clusters, cumulative effects become observable. More importantly, if galaxy clusters move collectively, this motion affects interaction intensity through Doppler effects, like ambulance sirens sounding higher when approaching and lower when receding. Moving galaxy clusters leave characteristic temperature signatures in cosmic microwave background. NASA Goddard Space Flight Center's research team, led by Alexander Kashlinsky, precisely utilized this effect to detect galaxy cluster motion. They needed to analyze data from over 1,000 known galaxy clusters, an extraordinarily complex and precise undertaking. This process resembles identifying individual instrumental timbres within symphonies. Cosmic microwave background radiation contains mixed signals, primordial density fluctuations, lensing effects, foreground contamination, etc. Extracting weak galaxy cluster motion signals from this mixture requires sophisticated statistical analysis and data processing techniques. When Kashlinsky's team completed their analysis, results shocked everyone. Data revealed these 1,000 galaxy clusters weren't moving randomly but exhibited obvious collective flow patterns. They all moved toward Centaurus and Hydra directions, forming a massive river spanning 2.5 billion light-years. This discovery's significance proves profound. According to standard cosmological models, at such vast scales, the universe should exhibit uniformity and isotropy. Galaxy cluster motion should primarily depend on local gravitational structures without displaying such large-scale coordination. Dark flow's existence suggests two possibilities. First, our understanding of cosmic large-scale structure remains incomplete. Massive undiscovered structures might exist. Second, beyond the observable universe's edge, enormous mass concentrations capable of influencing us might exist. If the second possibility proves correct, this would pose fundamental challenges to our cosmological models. It would mean the universe we observe might represent only a minute portion of a larger structure, like someone standing in a forest seeing only surrounding trees while unable to perceive the entire forest. To understand dark flow generation, we must return to the universe's initial moment. According to modern cosmological theory, the universe experienced a process called inflation, rapid expansion during extremely brief periods after birth. This process resembles a balloon being suddenly inflated, yet at unimaginable velocity and scale. Before inflation occurred, different cosmic regions might have possessed various non-uniform density distributions and gravitational fields. Perhaps in that distant past, our currently observable universe region was once influenced by some massive mass concentration, acquiring initial momentum toward that direction. Then cosmic inflation commenced. In less than 10 to the power of -32 seconds, cosmic scale expanded by at least 10 to the power of 26 times. This rapid expansion pushed that massive gravitational source beyond our observable range, making it now hundreds of billions or trillions of light-years distant. Yet, like rivers remembering distant mountain contours, early gravitational influences persist in galaxy cluster motion. These galaxy clusters continue moving toward that long invisible gravitational source, becoming living fossils of early cosmic history. This explanation sounds reasonable yet poses major challenges to standard cosmological models. Cosmic inflation theory's core prediction involves creating highly uniform and isotropic universe. If dark flow truly exists, it might mean either inflation theory requires revision or our inflation process understanding needs deepening. However, not all scientists agree on dark flow's existence. Science operates this way. Every major discovery faces rigorous scrutiny and verification. The European Space Agency's Planck satellite project team re-examined identical data using more advanced instruments yet reached different conclusions. Planck satellite launched in 2009, 8 years after WMAP, with superior technology. Its observational precision greatly exceeded maps, capable of detecting fainter signals. The Planck team employed identical Sunyaev-Zel'dovich effect analysis methods, studying the same 1,000 galaxy clusters, yet claimed finding no clear dark flow evidence. This scientific controversy proves fascinating, demonstrating scientific exploration's caution and rigor. When confronting such major discoveries, scientists require repeated verification to ensure they're not deceived by data noise, systematic errors, or analysis method problems. Kashlinsky's team wasn't deterred by this questioning. They reanalyzed Planck data, maintaining that dark flow signals truly exist, merely masked by more complex foreground effects. They also noted that different analysis methods and data processing techniques might influence results. This scientific debate reflects modern astronomy's fundamental challenge. Studied signals often prove extremely weak, buried within various noise and systematic effects. Extracting genuine physical information from such complex data requires extraordinarily refined analysis techniques and deep understanding of possible error sources. Should dark flow truly exist, it would pose fundamental challenges to our basic cosmic understanding assumptions. Modern cosmology builds upon a foundational assumption called the cosmological principle. At sufficiently large scales, the universe exhibits uniformity and isotropy. This principle resembles thoroughly stirred coffee. Though small-scale non-uniformities might exist like coffee bubbles, large scales should appear completely uniform. The cosmological principle represents both observational fact and foundation for numerous theoretical calculations. Yet dark flow's existence suggests that at immense scales, the universe might not prove as uniform as imagined. Like discovering what you assumed was a tranquil lake surface actually conceals massive underwater currents. Such discovery would compel us to re-examine cosmology's foundational theories. One possible explanation suggests our observable universe represents only a small portion within larger structure. Perhaps where we cannot observe, grander and more complex cosmic landscapes exist. We might resemble residents living in one neighborhood of a vast city, seeing only nearby buildings while unable to sense the entire urban layout. Another possibility involves dark matter and dark energy distribution proving more complex than imagined. Perhaps beyond the observable universe's edge, massive dark matter structures exist whose gravitational influence can cross cosmic boundaries, affecting galaxy cluster motion here. Some scientists propose even more radical theories. Perhaps we need to modify general relativity or introduce novel physical mechanisms to explain this large-scale motion pattern. These theories, though still immature, represent scientists' innovative thinking when confronting new phenomena. As observational technology continuously advances, our dark flow understanding gradually deepens. New generation space telescopes and ground-based observational equipment provide unprecedented observational capabilities. Though primarily designed for observing distant galaxies and star formation, the James Webb Space Telescope's high-precision observational abilities can also study large-scale structures. By observing more and increasingly distant galaxy clusters, we can better understand the universe's large-scale motion patterns. The Euclid Space Telescope represents a European Space Agency project specifically designed for studying dark energy and large-scale structures. It will map precise positions and morphologies of billions of galaxies, helping us better understand cosmic geometric properties and dynamic evolution. On Earth, new generation large survey projects also contribute valuable data. For example, the Dark Energy Survey Project and the forthcoming Vera Rubin Observatory Legacy Survey will observe hundreds of millions of galaxies, providing unprecedented statistical samples for studying large-scale structures. These projects' data prove not only vast in quantity but continuously improving in quality. Novel analysis techniques, including artificial intelligence and machine learning methods, are being employed to extract physical information from these complex datasets. Perhaps in the near future, we can finally resolve the controversy over dark flow's existence. The dark flow controversy transcends technical issues. It also touches profound philosophical questions. If dark flow truly exists, what does it signify? How does it alter our understanding of our cosmic position? First, dark flow's existence would remind us of human cognitive limitations. We tend to assume our observations represent complete reality, yet dark flow suggests massive structures and processes might operate beyond our perception. This realization proves both humbling and exhilarating. It means the universe proves more complex and fascinating than we imagine. Second, dark flow's discovery process demonstrates scientific methodology's power and limitations. Through precise observation and analysis, we can detect extraordinarily weak signals, inferring phenomena that might exist beyond observational boundaries. Simultaneously, different research teams reaching different conclusions reminds us that scientific knowledge builds gradually, requiring constant verification and revision. Dark flow also raises considerations about cosmic unity. If the universe exhibits non-uniformity at the largest scales, do physical laws discovered in different regions remain identical? Do physics theories we establish on Earth possess universality? These questions lack simple answers, yet they drive deeper contemplation about nature's fundamental laws. Regardless of dark flow's ultimate reality, it reminds us the universe remains filled with unsolved mysteries. Whenever we believe we understand cosmic fundamental laws, new phenomena emerge to challenge our cognition, propelling scientific advancement. In the near future, new generation observational equipment will provide clearer answers. Perhaps we'll confirm dark flow's existence, thus opening exploration of larger-scale cosmic structures. Perhaps we'll discover dark flow represents merely analytical phantoms. Yet this process itself will deepen our understanding of observational techniques and analysis methods. Looking further ahead, dark flow research might promote new theoretical developments. Perhaps we need to develop theories transcending general relativity or reconsider cosmology's basic assumptions. These theoretical breakthroughs might, like Einstein's relativity, completely transform our cosmic understanding. Dark flow's story also demonstrates international cooperation's importance in modern science. Scientists from different countries and institutions collaborate to construct advanced observational equipment, share data and analysis methods, jointly exploring cosmic mysteries. This cooperative spirit itself represents a highlight of human civilization. Standing at the observable universe's edge gazing outward, we resemble ancient navigators standing on shores contemplating the horizon. We know beyond that horizon lie more oceans and continents, yet we cannot journey there, only inferring their existence through indirect evidence. Dark flow represents such evidence, a mysterious signal pointing toward the unknown. Whether ultimately confirmed or refuted, it embodies human exploratory spirit. We remain unsatisfied with known boundaries, constantly attempting to transcend cognitive limits while seeking new knowledge and understanding. Perhaps one day our technology will advance sufficiently to directly detect beyond the observable universe's edge. Perhaps we'll discover massive structures there, explaining dark flow's origins. Or perhaps we'll uncover completely different truths, surpassing our current imagination. Regardless, this exploration of the unknown will continue eternally, because curiosity represents one of humanity's most fundamental traits, driving us to constantly transcend known boundaries while seeking new knowledge and understanding. Dark Flow's story reminds us that within this seemingly familiar universe, countless secrets still await discovery. In this tender universe, we exist as both minute and magnificent. Minute because we represent merely cosmic dust specks. Magnificent because we possess cosmic understanding capabilities and courage to explore the unknown. Let us carry this gentle curiosity and continue our cosmic exploration odyssey. Every discovery becomes a new poem. Every mystery opens doors to deeper truth. In this infinitely beautiful universe, our exploration never ends, and our wonder never ceases. Just as dark flow quietly courses at the observable universe's edge, human curiosity will flow eternally through knowledge's ocean until time's end